Hello, this is Zoya Pashpur from Civil Engineering Department of the University of Memphis. I'd like to speak about my research results about selection of ground motion models for probabilistic seismic hazard analysis in Iran. The ground motion models are the essential component of the probabilistic seismic hazard analysis, in which their validity is basically dependent on the sufficiency of the data. In the current practice of PSHA, the different estimates of the ground motions predicted by different empirical models are attributed to the epistemic uncertainty, which this uncertainty will be directly affected. For this study, we selected three data-driven methods for ranking the selected ground motion models. The first one is the log likelihood or LH method, which proposed by Sherbaum et al. 2009 as an information theoretic approach, which this method uses the Kullback-Leibler metric, or the distance between the expected value of the true model and the expected value of approximate model. The LLH measures the distance between two continuous probability density function, which the first one is the function which log normally distributed for the observed data point, and the second one is the estimated value that distributed log normally with the median and standard deviation for the considered model. The second one is the Euclidean distance-based ranking, or the EDR, which proposed by Kale and Akar 2013. This method uses the Euclidean distance, or the absolute difference between the observed and estimated data, to account for both aleatory variability in ground motions and trend between the observed and estimated data. And the third one is the deviance information criterion, which proposed by Kosari et al. 2019. And this method is using the deviance information criterion that optimize the selection of ground motion models using the Bayesian statistics framework. This model has two main assumptions for the modeling. The first one is standard deviation of the model is assumed to be known or denoted as period sigma, and this sigma is previously determined. And the second one is the standard deviation of the model is unknown and denoted as posterior sigma. The selected database for this study is obtained from Building and Housing Research Center of Iran. This database is an independent database which we used for test the capability of the candidate ground motion models. This database includes 201 records from 29 recent earthquake events happened in Iran, with magnitude ranging between 4.5 and 7.3, with distance up to 275 kilometers. I would like to add this. In this database, we have two recent destructive earthquake strong motion data, such as November 12, 2017 Ezgele earthquake with magnitude 7.3, and the Sarapol Zahab earthquake with magnitude 6.3, which happened on November 25th, 2018 in western of Iran. In this plot, I'm going to show you the geographic distribution of Iranian strike motion recording stations and the earthquake epicenters which we use in this study. The location of earthquake events showing by red circles and the stations showing by white triangles. Also, the location of two destructive earthquakes which mentioned in the previous slides are shown in this plot. For this study, we selected 5 local ground motion models which developed exclusively using Iranian strike motion data and 5 NGA West 2 ground motion models which developed from strike motion data worldwide. In this figure, the EDR, LLH, DIC1 scores with the prior sigma and DIC2 with the posterior sigma at selected periods for the candidates models is shown. The smaller scores imply better presentation of the observed ground motions by the predictive model. Also in the table, the prior and posterior standard deviation in natural logarithm of the candidate models at different periods are shown. Generally, the result shows the local ground motion models have better performance compared to the other models, and the result of the EDR is different than the LLH and DIC method, and it is biased towards ground motion models with smaller sigma. The behavior of NGA West 2 models is fairly similar, while Abrahamson et al. 2014 and Bohr et al. 2014 show a better performance. This figure is showing the distribution of residual for PGA versus distance and magnitude for the local ground motion model on the left side and the global ground motion model in the right side. As you are seeing in the left side, the local ground motion models underpredict the PGA of small earthquake and overpredict for the large earthquake, with the exception of the Zaffarani et al. 2018 and Darzi et al. 2019. But for the NGA West 2 models, the residual versus magnitude shows that the only unbiased model is Bohr et al. 2014 and Abrahamson et al. 2014. Furthermore, we plot the attenuation of the local model and global model versus distance and compare them with the observed data in this figure. As you are seeing in top row, we have local ground motion model attenuation, and the second row shows the NGA West 2 models at PGA for the 3 magnitude beams for magnitude moment magnitude 5, 6, and 7.3. The gray circles show the observed strike motion data, and the colored line showing the ground motion models attenuation. We also plot the median ground motion models that are ranked as the best model by using the IC2 plus minus its standard deviation at each period. This figure is also showing the attenuation of the candidate models. The first row is showing the performance of local model versus distance, and the second row is showing the performance of the NGA West 2 models versus distance and for Iranian database which we use in this study. The results of this study presented for PGA and PSA over the different selected range of periods. The result indicates that the best fit between the local models and observed data. And among these 5 candidate models for local grand motion model, the Farajpur et al. 2019 and Darzi et al. 2019 show the better fit versus the observed data, particularly at short periods. And Zafarani et al. 2018, Sadaqati and Pezesh 2017 are preferable. Moreover, the Kale model show better performance at long periods. And as part of this study, we work on the 3 data-driven method and the EDR and LLH methods favor models with smaller and larger sigma, respectively, regardless of what the true uncertainty is. In contrast, the DIC method that uses Bayesian statistics is shown to optimize the grand motion selection for a given region, leading to an unbiased assessment of earthquake hazard. The DIC method offers an advantage of partially removing the ergodic assumption from the grand motion model selection process when the grand motion recording are homogeneously distributed in terms of magnitude and distance. The authors would like to thank from the Building and Housing Research Center BHRC of Iran that provides strong grand motion records for this study. And at the end, the full text of this study is available in Bulletin of the Seismological Society of America. Thank you for your attention.